Hi everybody. In this video I will be discussing about Ostwald's dilution law and ionic product of water. In case if you like this video, do check out other videos of this playlist as well. Without wasting any further time, let's get started. Now in Ostwald's dilution law, the first thing we take is a weak acid. Say for example, if it was a strong acid like hydrochloric acid, HCl. If you take 5 moles of HCl and put it in water, all of them will dissociate, giving you H plus and Cl minus. In case of a weak acid, something like acetic acid, CH3COOH, if you take 5 moles of acetic acid, then only 1 mole or maybe even lesser than 1 mole will dissociate, giving you H plus and CH3COO minus. Most of CH3COOH will remain in the undissociated form. So the law that we are learning is applicable for weak acids and weak bases only. So let's start applying this law for a weak acid first. Let's take the weak acid, which is acetic acid, which is CH3COOH. Now saying CH3COO will be very long every time. So instead of CH3COO, let's just in general call it A. So let's take a weak acid, that is AH. And that weak acid AH is what we are putting in water. So AH plus water. Now I am writing a reversible reaction because entire HA or entire AH will not dissociate into H plus and A minus. A part of it will dissociate, whereas most of AH will remain in the undissociated form because AH, like I said, was a weak acid. So after dissociation, you will have H plus and A minus. But H plus actually combines with water and forms H3O plus. That is how H plus exists in reality. H plus does not exist in the independent or the free form. So we will have H3O plus A minus. That is how the equilibrium reaction will be existing in the solution that you have taken. Let us say, for example, we have taken 1 mole of HA and initially we did not have any H plus or any A minus in the solution. Let us say that the degree of dissociation is alpha. Now when we say degree of dissociation, let's say for example I had taken 5 moles of some acid or 5 moles of an electrolyte, and out of 5 moles, if 2 moles are going to dissociate, then alpha will be written as 2 upon 5, which is 0.4. So we can say that degree of dissociation alpha is actually the fraction of the number of moles that have dissociated. Fraction of the number of moles dissociated means total number of moles dissociated divided by the number of moles that you had originally taken. And if you consider that 0.4, it's like 0.4 upon 1. You can also say alpha actually represents that how much out of 1 mole is going to get dissociated. So I have taken 1 mole of AH, and let us say that when equilibrium is established, alpha moles of AH have dissociated into H plus and A minus. At equilibrium, if alpha moles of AH are going to dissociate, then I will be left with 1 minus alpha moles of AH with me. And say for example, if I take a pen, okay, break that pen. If I break one pen, I get one body and one cap. In a similar way, if alpha moles of AH have dissociated, you will have alpha moles of H plus and alpha moles of A minus. A common mistake made over here is that if alpha moles of AH dissociate, we will get alpha by 2 of this and alpha by 2 of this. Don't make that mistake. Just think over it a little bit. You will realize that if alpha moles of AH dissociate, you will have alpha moles of H plus and alpha moles of A minus. So these are the number of moles of each of the species that you have at equilibrium. Now if I tell you to write the equilibrium constant for this reaction, you will write it like this. K, that is the equilibrium constant for this reaction, will be H3O plus, and for all practical purposes or all calculation, all theory purposes, we write H3O plus as H plus only. So we have H plus into A minus. These terms actually mean concentrations. In case you do not have any clue about what I am doing, then do check the part 1 of this video, because there I have discussed in detail about what the equilibrium constant is. So go ahead, H plus into A minus, that is their concentrations, divided by the concentration of reactants, which is concentration of AH, into concentration of H2O. Now say for example, the volume of water that I have taken is 1 liter. Let's say everything is happening in a volume of 1 liter solution. That is, let's say I have taken 1 liter of water. So if I have 1 liter of water, that will be 1000 ml of water, and 1000 ml of water is like 1000 grams of water. 1000 grams of water is 1000 divided by 18, that is roughly 55-56 moles of water. Now if I have 55 moles of water and 1 mole of water is reacting in this reaction, or let's say alpha moles, right? Alpha moles have reacted, so alpha moles of water are getting reduced. Now alpha will be a very small number, a number much lesser than 1. So if there were roughly 55.5 moles of water, maximum 1 mole can react. So the concentration of water will be 54. My point is that because water is present in excess, the change in concentration of water is very less. At the most it is going from 55 to 54. These are not the exact numbers, but I am just giving you an example. The point is, because water is present in excess, its concentration will be constant. And because that concentration is constant, I can take that constant on the left hand side. So we will have H2O multiplied by K equal to this expression. Now one constant into the other constant will be a third constant, and let's call it Ka. And that Ka will be H plus into A minus upon Ha. Now keep in mind, what was K? It was the equilibrium constant. The equilibrium constant which I get for this reaction after multiplying with water is what we call dissociation constant. Because this was the dissociation reaction, we call Ka the dissociation constant of the weak acid Ha. The dissociation constant is simply given by H plus into A minus upon Ha. Keep in mind that while writing the dissociation constant of an acid, you do not include H2O over here. That H2O was constant, it has already gone on the left and got combined with K, and that combination of H2O with K gave you Ka, which was the dissociation constant of the weak acid. Now we need to put in the values over here so that we can derive a final formula for Ostwald's dilution law. Check over here. H plus is the concentration of H at equilibrium. At equilibrium, we have alpha moles of H plus. Let us say that the entire solution is having a volume of V liters. Everything is happening in a solution of volume V liters. So the concentration of H plus at equilibrium is alpha upon V, because concentration is number of moles per unit volume. So number of moles are alpha. I said volume of the solution is V. So concentration of H plus will be alpha upon V, multiplied by concentration of A minus will also be alpha upon V. The full thing divided by the concentration of AH, and that is going to be 1 minus alpha the whole upon V. You can cancel out a V here and a V here. That will leave you with alpha square upon 1 minus alpha the whole into 1 upon V. Now what is that 1 upon V? You had taken 1 mole of HA with you initially, and concentration is number of moles per unit volume, but number of moles is 1. That is what you had initially taken. So concentration is 1 upon V. So the concentration of HA is 1 upon V, and that is why I can replace that 1 upon V with C. So I get alpha square upon 1 minus alpha the whole into C, and that is the final formula that you need to remember. That is Ka, which is the dissociation constant for a weak acid, is written as alpha square C upon 1 minus alpha. Now there are certain rearrangements that can happen with this formula. That is, I said that HA was a weak acid, but because HA is a weak acid, the number of moles of HA that will dissociate will be very less. So alpha will be very small compared to 1, and that is why 1 minus alpha can be approximately written as 1 only. So if we write 1 minus alpha approximately as 1, we can say Ka will be alpha square into C upon 1 minus alpha, which is 1. So this is another formula that you can use. Now most often the formula used is Ka is alpha square into C, but in JEE mains there was one question where they were actually expecting you to use this formula. Now this formula was being used because alpha, the value of alpha that the question had given, was not negligible, and because alpha is not negligible you had to use this formula. But often students make a mistake that they memorize this formula, and in circumstances where alpha is not very small, they use this formula and end up making a mistake. So keep in mind, you can use this formula only if alpha is very less than 1. In all other cases, you will have to use this formula. Now we get to that Ostwald's dilution law, the actual statement of it. For understanding the statement, you need to rearrange this formula. If you rearrange this formula, you will realize that the value of alpha is turning out to be root over Ka upon C. So this is where the Ostwald's dilution law statement can be made. That is, the degree of dissociation of a weak acid is inversely proportional to the square root of concentration. This is where some students often ask me that it is directly proportional to Ka also. Why don't we say alpha is proportional to Ka? Keep in mind, what was that Ka? Ka was actually a form of equilibrium constant, and in the part 1 of this video, I had mentioned that this equilibrium constant depends only on temperature. That is, if the temperature changes, then K will change. But other than temperature, no matter whatever in the world you change, this K value will remain what it is. So Ka is also a form of equilibrium constant. It will change only if the temperature changes. Anything else changes, the value of Ka will not change. For example, the value of Ka is 5. Now Ka will not be 5, it will be something else, but let's say suppose Ka for some reaction is equal to 5. If you change H plus A minus HA, this 5 will never change. If you try to change H plus, then the reaction will change H plus A minus and HA in such a way that the numbers, their multiplication will finally be equal to 5 only. That is, the Ka value will not depend upon the concentrations. No matter how much ever you change the concentrations, the reaction will try to change the concentrations once again in such a way that their multiplication turns out to be equal to that constant value of Ka. Okay, so Ka for any given reaction is a constant. For any given acid, I can say Ka will be constant, and that is why alpha will be inversely proportional to the square root of concentration, and that is your Ostwald's dilution law. It is often stated in this way also. We said that 1 upon V was equal to C, so you can write that 1 upon C as V, and you can claim that this is Ka multiplied by V. So Ostwald's dilution law can also be stated as the degree of dissociation of a weak acid is directly proportional to the square root of the volume of the solution. So you can call it proportional to root V, or you can call it inversely proportional to root C. I am sorry, it is proportional to the square root of the volume of the solution. Okay, so that is the statement of Ostwald's dilution law. It's not important to memorize the statement. What is more important is to understand the calculations over here. Also, certain important things to understand are, like I said, Ka will depend only on temperature, and also keep in mind that the H plus A minus and HA, the values that I have substituted for their concentrations are the concentrations at equilibrium. So this is how you can explain Ostwald's dilution law for a weak acid. Let's now derive the Ostwald's dilution law for a weak base. The steps are going to be the same as the ones for a weak acid, so we will go a little fast with this. Take a weak base. A base means something that gives OH minus ions. So instead of HA, this time we will call it BOH. So BOH is the weak base, and when you put it in water, the dissociation will be of the type B plus OH minus. So you can then say that the K value will be B plus into OH minus, the whole divided by BOH into H2O. It is the multiplication of the concentration of products divided by the concentration of reactants. That H2O will remain a constant because H2O is present in excess. That constant goes here, gets multiplied with K, and the final constant is what you will call Kb. And Kb is the dissociation constant for the weak base. Now the value of Kb can be written as, if you have initially taken 1 mole of BOH, you had nothing of B plus and OH minus, and if the degree of dissociation is alpha, that means out of 1 mole, if alpha moles dissociate, then at equilibrium, you will have 1 minus alpha moles of BOH, you will have alpha moles of B plus and alpha moles of OH minus. So that will give you B plus concentration as alpha upon V. We are considering that the volume of the solution is V and the number of moles we had was alpha, and that is why the concentration at equilibrium is alpha by V. For OH minus also the concentration is alpha by V, and for BOH it is 1 minus alpha the whole upon V. This becomes alpha square upon 1 minus alpha the whole into 1 upon V, and that 1 upon V can be written as C. So that is the value for Kb for a weak base. The other variations like I have discussed, you can put that 1 minus alpha approximately equal to 1, assuming that the base that you have taken is a weak base, and because it is a weak base, the amount dissociated will be negligible. That is why alpha will be negligible and 1 minus alpha will be approximately equal to 1. So you can write that 1 minus alpha as 1 and Kb can be written as alpha square into C. Like I said, keep in mind that this formula is applicable only if you are neglecting alpha. If you are not neglecting alpha, then it's important to remember this formula. And alpha will be neglected only if alpha is very less than 1. And if alpha is not less than 1, or if alpha is something like 0.4 or 0.5, you cannot neglect alpha and you need to use this formula. Okay, so that is about derivation of Ostwald's dilution law for a weak base. And like I said, for writing the statement, you should rearrange this formula. So again, alpha will be root over Kb upon C, and you can say that the degree of dissociation of a weak base is inversely proportional to the square root of its concentration, or directly proportional to the square root of the volume of solution. Before we move on to the next concept, let us just cover this one small thing. Say for example, in your solution, you have concentration of your weak base BOH or even your weak acid HA, either of them. Its concentration is say for example 5 moles per liter. Now let us say the degree of dissociation is alpha. That is, out of 1 mole, alpha moles will dissociate, and if out of 1 mole alpha moles are dissociating, then you will get alpha moles of either H plus or alpha moles of OH minus, depending upon whether you have taken a weak acid or a weak base. So if it's a weak acid, let's go ahead with acid H plus. I said you have alpha moles of H plus if you had taken 1 mole of the weak acid HA, but currently what you have is 5 moles in every 1 liter of the solution. If 1 is giving you alpha moles of H plus, then 5 are going to give you 5 alpha moles of H plus, and that 5 alpha will be present in 1 liter. So I can say that the H plus ion concentration, if it's a weak acid, will be 5 alpha moles per liter. Now you got 5 alpha because the concentration was 5. In general, if the concentration is not 5, it is simply C, then you can say that the H plus ion concentration will be C alpha. So that's the formula I need you to understand. It's okay if you memorize it, but like I've said, it's not good to memorize things. It's just best that you understand it. So this is simple. It's a simple logic that H plus ion concentration will be C alpha if it's a weak acid, and if it's a weak base, then OH minus ion concentration, with the same explanation we can say, will be equal to C alpha, where alpha is degree of dissociation of that weak acid or weak base, and C is the concentration of the original base or the original acid that you had taken. If you're clear with this, let's get started with the next. The next thing that we are discussing is called ionic product of water. Now whatever you have done with an acid, I need you to do the same thing with water. Say for example, you take simple ordinary water, which is H2O. Then if there is dissociation of water, water will dissociate as H plus and OH minus. You may be wondering that this does not happen, like water is not a strong electrolyte. Water will never dissociate giving H plus and OH minus by itself. But in theory, in reality, it so happens that if you take a large amount of water, then a very little amount of water does dissociate, giving you H plus and OH minus. So say for example, if you have taken, I'll tell you the numbers later on, but for the time being, let's just say that water very little will dissociate, giving you H plus and OH minus. Now if you try to apply the equilibrium constant for this reaction, that equilibrium constant K will be written as H plus into OH minus divided by concentration of H2O. But again, like I said, if you take a large amount of water, then only a very little part of it will dissociate, giving you H plus and OH minus. So the concentration of water will not get affected. It's like the numbers go like this. If you take 1 liter of water, then in 1 liter of water, only 10 power minus 7 moles of water will dissociate. So if 10 power minus 7 moles of water have dissociated in 1 liter, then you will have 10 power minus 7 moles of H plus and 10 power minus 7 moles of OH minus. in 1 liter of water. Now like I said, 1 liter of water is 1000 grams, which is 1000 upon 18, that is 55.5 moles of water. Now out of 55.5 moles of water, only 10 to the power minus 7 moles of water have dissociated. So the concentration of H2O from 55.5 changes to 55.55 minus 10 power minus 7, which is almost 55.55. The point over here is concentration of water is almost constant, and when that constant goes on the left, it gets multiplied with K, giving you another constant. We call it Kw. And that Kw is what we say is ionic product of water. Which is actually equal to H plus. You are left with H plus and OH minus here. So H plus into OH minus. Now you may be wondering that this is exactly the thing that we had done for an acid, but when we did that for an acid, we called that K dissociation constant of the acid, and here we are calling it ionic product of water. See, the concept is, there the original reaction, this reaction, in the previous case was dissociation for an acid, and that is why we called it dissociation constant of the acid. Here the reaction is dissociation of water, and because it is dissociation of water, we are calling it ionic product of water. And ionic product also, the other reason is, it is H plus into OH minus. It is the product of ions that are present in pure water. So simply call it ionic product of water. Now think over it, what is that ionic product? Again, that ionic product is a form of equilibrium constant only, and like I have said, equilibrium constant, no matter whatever in the world changes, equilibrium constant's value will not change. So Kw's value will remain constant no matter how much ever you change H plus or how much ever you change OH minus. Kw will change only under one case. Kw will change only if temperature changes. That is, only if the temperature goes up or goes down, Kw will vary. Other than that, the value of Kw will remain constant. At 25 degrees Celsius, I said that out of 1 liter of water, in 1 liter of water, only 10 to the power minus 7 moles are going to be present of H plus as well as OH minus. So the concentration of H plus is 10 to the power minus 7 moles. The volume we have taken is 1 liter. So the concentration is 10 to the power minus 7 moles upon volume in liters, that is 1, which is 10 power minus 7 only. So we can put H plus as 10 power minus 7 multiplied by OH minus, which is also 10 power minus 7, and that makes it 10 power minus 14. So at 25 degrees Celsius, the value of Kw is 10 to the power minus 14. Now think over it, what if I increase the temperature? The question is, if I increase the temperature, will Kw increase or it will go down? Like I said, Kw depends only on temperature, right? So for answering this question, you need to think over it like this. Say for example, there is a bond. If I supply energy, the bond breaks. In reverse, I can say that if the bond is formed, energy will be liberated. I give energy, bond breaks. If a bond is formed, energy will be liberated. So now, when you say H2O's dissociation, is it bond breaking or bond forming? It is very clearly bond breaking between H and OH. So for bond breaking, you need to supply energy. So plus energy, and that energy is actually heat energy. So heat energy plus H2O is going to give you H plus plus OH minus. Now you are increasing the temperature. If you increase the temperature, you are giving heat, and like I had mentioned in the part 1 of this video, as per Le Chatelier's principle, if you increase the temperature, then the equilibrium will shift on the other side. So H plus and OH minus will be formed in a higher extent. Now the H plus and OH minus values, after you supply heat, will be more than 10 power minus 7, something like, let's assume 10 power minus 6. So the ionic product of water will become 10 power minus 6 into 10 power minus 6, that is 10 power minus 12. And that 10 power minus 12 is greater than 10 power minus 14. So by increasing the temperature, the Kw value is going to increase. Now this does not happen in every case. Of course, in most of the cases, K value will increase with an increase in temperature, but some places, somewhere it might even decrease. As far as water is concerned, Kw, that is ionic product, will increase as temperature increases. That's yet another thing I need you to understand. Now, there is one thing over here we define, something called pH of a solution. pH of a solution means negative log to the base 10 of the concentration of H plus ions. In a similar way, you can define something called POH and pKw also. So we will say POH is negative log to the base 10 of OH minus ions, and pKw is minus log of Kw to the base 10. Can you tell me the values of POH, pH and Kw for this particular case for pure water? We can say that for pure water, of course at 25 degrees Celsius, the pH value will be, here you just need to put 10 power minus 7. When that minus 7 comes down, minus of minus 7 will be 7, and we have 7 log 10 to the base 10. Log 10 to the base 10 is 1, so pH value will be 7 for pure water. Similarly, POH will be equal to 7 and pKw will be equal to 14. You can just put in the values of pH, POH and pKw. You can put in the values of H plus, OH minus and Kw in the equations here. You will realize that pH and POH will be 7, pKw will be 14. So we can conclude over here that pH plus POH will always be equal to pKw. If that explanation is not convincing, you can actually take a minus log to the base 10 here. So minus log to the base 10 on the left will give you pKw on the left, and on the right hand side it will be minus log to the base 10 of H plus into OH minus. You can split that and write it as minus log of H plus to the base 10 plus minus log OH minus to the base 10. So that will be pH plus POH. Yet another result you need to keep in mind. Let's take some questions based on whatever results you have just learned. Say for example, I ask you to find the pH of 0.01 molar HCl solution. So you will tell me that HCl is a strong acid. It will dissociate completely in water, and because the concentration of HCl was 0.01 molar, we will have the concentration of H plus ions also as 0.01. So the H plus ion concentration becomes 0.01 molar, and the pH will be minus of log to the base 10 of the concentration of H plus ions, that is of 0.01, and this is 10 power minus 2. That minus 2 comes out and gives you the pH value equal to 2. Agreed. That is the way you have been solving sums till now. Fine. But you need to think a little bit deeper, okay? This is not the way you should learn a concept and then just find answers by putting in numbers in the formula. Just try to think whatever is happening over there and correlate it with the concept you have learned. Say for example, in the same solution, what if I ask you to find POH? This is where certain students often come up with an answer that, sir, pH plus POH is equal to pKw. So pH plus POH, you just learned it was pKw, and the value for pKw at 25 degrees Celsius is 14. So let's assume everything is at 25 degrees Celsius and this value will be 14. You got pH for the solution as 2, and that is why POH will be 12. It's the right answer, fine. But then if you think a little, this is an acidic solution. How do you get OH minus in an acidic solution? Because see, POH ultimately was minus log to the base 10 of OH minus ions. So if minus log of OH minus to the base 10 is 12, the OH minus ion concentration is something in the solution. So that is what my question states, that if it was an acidic solution, how come in an acidic solution were you getting OH minus ion concentration? This is where you need to get back to that equation. You had written the ionic product of water Kw. So think about what you have done in the entire question, okay? You have actually taken 0.01 molar HCl solution. Think about how did you make that solution. For making that solution, let's say you took 1 liter of water, and in that 1 liter of water, you will add 0.01 moles of HCl. That is what will give you this solution. So before putting that HCl, you had pure water, and in pure water, the Kw, that is ionic product of water, is H plus into OH minus. Keep in mind, this is a type of equilibrium constant only, so its value will remain constant as long as the temperature is constant. So it is Kw equal to H plus into OH minus. As long as it was neutral water, the H plus that I had was 10 power minus 7 and the OH minus I had was also 10 power minus 7 and the ionic product of water was 10 power minus 14, and this will remain constant. No matter whatever I keep changing in the solution except temperature, this will remain 10 power minus 14 only. You are putting 0.01 moles of HCl. So that is, you are putting 0.01 moles of H plus. Now the number of moles of H plus that you have after putting HCl are 0.01 plus 10 to the power minus 7 and OH minus were also 10 to the power minus 7. The problem that arises is that now the product of H plus into OH minus is not 10 to the power minus 14, it is much greater than that. Will the solution allow you to do that? The answer is no, because no matter whatever you change other than temperature, you're not changing the temperature, right? So because you're not changing the temperature, the Kw value has to remain 10 power minus 14 only. So the solution that you have made in water will try to bring H plus into OH minus as 10 to the power minus 14. How will that solution try to make the product as 10 power minus 14? See, the ionic product has gone up. 0.01 plus 10 to the power minus 7 is approximately 0.01 only. And 0.01 into 10 to the power minus 7 is 10 to the power minus 9, much greater than 10 to the power minus 14. So the product which you have needs to be decreased. And how do you decrease the product? The product will be decreased when you try to decrease H plus or you try to decrease OH minus. How do you decrease H plus or OH minus? You combine H plus and OH minus, they will form water. And that is how you are decreasing H plus and OH minus values. So let us say, for example, out of 10 power minus 7 moles of OH minus that you had, X moles of OH minus are combining with H plus. So I will have OH minus as 10 power minus 7 minus X, because X moles have now combined with H plus, and the H plus ions that I will have will be 0.1 which I had put, 0.01 which I had put, plus 10 to the power minus 7 which were already present initially. But if X moles of OH minus have combined with some moles of H plus, one OH minus combines with one H plus, so X will combine with XH plus. So minus X will happen over here as well. And at equilibrium, these are the final number of moles that I have of H plus and OH minus, and what you need to find is the final OH minus ion concentration. The OH minus ion concentration is 10 to the power minus 7 minus X, call it K. So the OH minus ion concentration is K, and this term 10 to the power minus 7 minus X will also be K. So I have 10 to the power minus 14, because this will never change. I said it's K, it's the equilibrium constant, right? So 10 to the power minus 7, 10 to the power minus 14 equal to, this would be 0.01 plus K, the whole multiplied by K, equal to 10 to the power minus 14. Again think over it. What was that K? It was 10 power minus 7 minus X. What was X? X was the number of moles of water of OH minus that got combined with H plus. So 10 to the power minus 7 minus X will be a little smaller than 10 power minus 7. Now this number K is smaller than 10 power minus 7, and 10 power minus 7 itself is much smaller than 0.01. So this number K, which is already smaller than 10 power minus 7, and 10 power minus 7 which was way smaller than 0.01, tells us that the number K will be much smaller than 0.01. And because K is much smaller than 0.01, 0.01 plus K will be approximately 0.01 only. So we get 10 power minus 14 equal to 0.01, that is 10 power minus 2 multiplied by K, and that is why we get K as 10 power minus 12, and that is your final OH minus ion concentration. And because the final OH minus ion concentration is 10 to the power minus 12, in that solution which was made in water, the pOH value, that is minus log to the log of OH minus to the base 10, will be the minus log of this, minus log to the base 10 of this, which will be equal to 12. See, you can apply the formula and get the result, but this much imagination is what you require, that this is what is actually happening inside the solution. Understand the full thing, and after this it is okay if you apply the formula, but don't directly go for applying the formula. Understand the full thing and then try to apply the formula. That will help you get the answers in a better way. Because say for example, this was a very easy question. If I twist the question, then these are the things you need to imagine. Like I'll twist the question and I'll show you. But before you go to that part, just see if you have understood the full thing. Try to reprocess the entire calculation in your mind. If you have not understood any specific part, rewind the video and watch it again. And if you are clear with this, we'll go ahead with the next question. Let's go ahead with the next question. Say for example, I tell you to find the pH of 10 to the power minus 8 molar HCl. Now here if you directly apply the result, you tell me that HCl is a strong acid, completely dissociates, so the H plus ion concentration will be 10 power minus 8 and pH will be minus log to the base 10 of H plus ion concentration, that is minus log to the base 10 of 10 to the power minus 8, which is equal to 8. So pH equal to 8, and then if you tell me pH will be 8, you are making a mistake, because pH equal to 8 would indicate it is a basic solution, and this can never be a basic solution. So in these circumstances, you again need to get back to that original way of thinking. So Kw is the ionic product of water, and we write it as H plus into OH minus. So if you think the way by which you were preparing the solution, you took some pure water, and in that pure water you are adding 10 power minus 8 moles of HCl, and before you had added HCl, H plus was 10 power minus 7. Kw, as you know, at 25 degrees, 10 power minus 14, H plus 10 power minus 7, and OH minus was also 10 power minus 7. But now since you have added 10 power minus 8 H plus, the H plus will be plus 10 power minus 8, and a part of it will recombine, so that if you have increased H plus, then now OH minus and H plus will combine, they will reduce a little till the ionic product again becomes equal to 10 power minus 14. So let us say that the combined amount is minus X. So OH minus will be 10 power minus 7 minus X. Now you can actually solve the entire equation, that is 10 power minus 14 equal to 10 power minus 7 plus 10 power minus 8 minus X, the full thing multiplied by 10 power minus 7 minus X, and get the X value. But that's not what you have to do. This is only a thing you need to understand. Now all you need to think is, what is the H plus ion concentration? The H plus ion concentration now is 10 to the power minus 7 plus 10 to the power minus 8 minus X. I know X is unknown and it will be difficult to find the X value, so this is where you need to go ahead with some approximations. See, it was H plus and OH minus, both were 10 to the power minus 7. You added very little H plus, so this value increased slightly. So this value will decrease slightly such that their product is equal to 10 to the power minus 14. So the reduction of OH minus was very little. That is, the reduction was X. X is very small, and because that X is very small in compared to these two numbers, you can actually say that this plus this minus X will be approximately equal to this plus this only. You cannot neglect 10 power minus 8 with respect to 10 to the power minus 7, because this is not negligible as compared to this. This addition of numbers will give you 1.1 into 10 to the power minus 7, because you can write 10 to the power minus 8 as 0.1 into 10 power minus 7, and finally you take minus log to the base 10 of this. So pH will now be minus log to the base 10 of H plus, which is 1.1 into 10 to the power minus 7, and that will be, if you split that, that will be minus log to the base 10 of 1.1 minus log to the base 10 of 10 power minus 7, which will be minus log to the base 10 of 1.1 plus 7. And this minus log to the base 10 of 1.1 might be something like 0.1 or so. So 7 minus 0.1 will give you roughly 6.9. And that is the final pH of this solution. See, we are definitely done with the examples I wanted to discuss. But there is one more thing I want you to really focus on in the calculations that we are doing. This is where some students often get confused with this particular point. So this is why I am discussing the point in a little detailed manner. Now, whenever you were solving the questions, you were applying the concept of ionic product of water. But when you learned ionic product of water, you learned it only and only for pure water. So whenever you are making a solution, how is it that you are able to apply the same concept for ionic product of water? So for that purpose, imagine this. If it was pure water, the dissociation was H plus plus OH minus, and you were able to write the Kw value as H plus into OH minus. In the same solution, let us put acetic acid, and we know that acetic acid is a weak acid. Now instead of acetic acid, take in general any weak acid. So take a weak acid and put it in the same solution. That weak acid will also dissociate in the same solution, and that dissociation will be HA in equilibrium with H plus plus A minus. Now for this dissociation also, you can write the equilibrium constant as K is equal to H plus into A minus upon HA. And these are things that you call dissociation constant of the weak acid, so you write it as Ka. Now these two are happening in the same solution. Because they are happening in the same solution, in spite of them happening in the same solution, you can write the individual K expressions for each of them. The presence of this will not affect this, and the presence of this will not affect this. The equations of K for both of them can be written because both of them are actually dissociations happening. No matter, even if they are happening in the same solution, the terms here will not appear here, neither the terms here will appear over here. The equations can be independently written of each other in spite of both the dissociations happening in the same solution. But then where does that effect of one on the other appear? That effect appears here. I had mentioned that the K value will remain constant, right? Here also, in spite of both the dissociations happening in the same solution, the K value will remain the same for both of them. That is, this will remain 10 power minus 14 only. And if Ka value is fixed at something like, just randomly take 10 power minus 10, for this acid, if the Ka value is 10 power minus 10, then Ka value will remain 10 power minus 10 for this acid also, no matter whatever else comes in the solution. But now, the terms here will get affected. They will get affected like this. Say for example, X moles of H2O dissociate. So they will give you X moles of H plus and X moles of OH minus. And over here, let's say Y moles of HA will dissociate. So that will give you Y moles of H plus and Y moles of A minus. Now whenever you are putting H plus, the value of H plus over here that you put will not be the one that you have obtained from this equation only. Listen to this point very carefully. You have written this equation for this dissociation, but the H plus value you put here will not be the H plus that you get only from this equation. It will be the H plus which is present in the entire solution. In the entire solution, H plus comes because of this as well as this. So the H plus value that you put will be X plus Y. This is the most important point I want you to understand. That is, the concentration that you put will be the concentration of that particular species present in the entire solution, and not the concentration that you get only from this equation, in spite of that equation being for this dissociation. Okay, so the OH minus value you put will also be the OH minus present in the entire solution. In the entire solution, OH minus comes from here only. There is no OH minus because of this, and that is why the OH minus value that you put will be only and only X. So X into X plus Y will be 10 power minus 14. Can you try writing the value for this? So 10 power minus 10 will be H plus in the entire solution. That will be Y because of this and X because of this. So that will be X plus Y multiplied by A minus, and A minus comes only because of this. So that will be Y. So X plus Y into Y upon the HA concentration. Let's assume we had taken some 1 mole of HA initially, and out of 1 I said Y dissociated. So the moles of HA I have with me are 1 minus Y. Now these are not moles that I should write. I should be writing them as concentrations, but assuming that the entire thing is happening in a solution of volume equal to 1 liter, the number of moles, if they were X, the concentration is X upon 1. And so will the other terms be X upon 1, Y upon 1, and the denominator for concentrations will be upon 1 only, and that is why the values will be these. So these are the ways you are substituting terms in the equation. Let me just repeat that final point which I want you to focus on. The final point is this, that in a solution, if there are a lot of components present, the equilibrium equations can be written for each component. and you can write the K values, the dissociation constants also for every component. The K value will remain fixed for every component irrespective of whatever is present in the solution. But the concentration value that you put will be the concentration value of that species present in the entire solution and not the concentration which you get from its own equation only. If it was X from this equation, you don't put it as X. You put it as the concentration present in the full solution, which is X plus Y. Okay, so I hope that point is clear, guys, and this is where I am done with covering whatever I wanted to cover in this video. I hope that these things were helpful to you and also that you have enjoyed this video. Thank you for watching, guys, and like I said, I hope this was helpful in your preparations.